The Greenland ice sheet is shedding billions of tons of meltwater into the ocean every year. While rising tides are the most visible consequence, the specific danger here lies in the water's chemistry. This runoff is almost entirely fresh, and that lack of salt is what threatens the physics of the ocean. This freshwater dumps directly into the Atlantic Meridional Overturning Circulation, or AMOC. It functions as a massive oceanic conveyor belt, connecting the deep north to the tropics. By pumping freshwater into this specific region, we are disrupting the ocean's global heat budget, the mechanical balance of energy transfer that maintains our modern climate. This visualization maps where the ocean absorbs intense solar energy. The cluster along the equator represents a gain of up to 1 petawatt of heat. Ocean currents physically transport that absorbed tropical heat northward, radiating warmth across the Atlantic toward Europe. A physical bottleneck exists at the end of the line. To make room for more warm water arriving from the south, the cold water in the North Atlantic must sink to the ocean floor. For this sinking process to function, the water must be incredibly dense and heavy. The mild climate enjoyed by millions of people relies exclusively on North Atlantic water remaining heavy enough to plunge toward the abyss. This is the thermohaline circulation. The name describes its two physical drivers, temperature, or thermo, and salt, or haline. On the trip north, evaporation makes the water saltier. Once it reaches the Arctic, the cold air strips away its heat, leaving it near freezing. This freezing, hyper-salty water becomes so dense that it plummets into the deep ocean, creating a massive volume known as North Atlantic deep water. This downward plunge creates a mechanical vacuum. As the dense water sinks, it actively pulls the next batch of warm equatorial water northward to replace it. This localized sinking process serves as the physical engine driving the planetary heat pump. Melting Arctic freshwater is significantly lighter than saltwater, and that difference in density creates a critical problem. When lightweight freshwater pours into the North Atlantic, it refuses to sink. Instead, it sits on the surface like a physical lid. Climate models show the AMOC can absorb small amounts of meltwater, but it eventually reaches a tipping point. Around 0.3 to 0.4 spur drops of freshwater forcing, the strength of the circulation abruptly collapses. As these cross-sections of the overturning circulation show, the water column loses its density at the threshold, causing the deep convection mechanism to shut off. The ocean undergoes stratification. The surface water and the deep ocean become separated into two completely uncoupled layers. With the freshwater lid blocking the way, the planetary heat pump grinds to a halt. The first mechanical impact happens along the U.S. East Coast. Without the sinking water to maintain the ocean's geostrophic balance, the currents physically alter their shape. This causes water to literally pile up against the shoreline. The result is a dynamic sea level rise of up to a meter, entirely independent of global ice melt volume. At the same time, regional temperatures in northern Europe will drop as the supply of equatorial heat is cut off. This cooling triggers an ice albedo feedback loop. New sea ice reflects more sunlight away from the surface, compounding the chill and potentially dropping local temperatures by 10 degrees Celsius. By breaking the heat budget, we shift the beneficiaries of the ocean's warmth into an era of severe, localized cooling. Thermal energy that can no longer move north becomes trapped in the global south. This cross-section shows the intense heat building up in the southern and equatorial latitudes. This trapped energy alters global wind patterns, dragging the intertropical convergence zone, the Earth's primary rainfall belt, farther south. Shifting this rainfall belt changes the agricultural reality for billions of people who rely on tropical weather patterns for food. These ice cores contain physical proof that this mechanism is real. Records of previous AMOC disruptions show climate swings of 8 to 16 degrees Celsius occurring in as little as a single decade. Diluting salt levels in the North Atlantic effectively chokes the intake of the global heat pump, stalling the mechanical process that governs our modern climate.